Today, we're tackling a problem that asks us to identify which words can be constructed using a limited set of characters, then sum their lengths. It's a straightforward task on the surface, but the efficiency of your character checking is critical. Given an array of strings called words and a string of available chars, we need to find all words from the words array that can be formed using only the characters in chars. Each character from chars can be used at most once for each word. Our final output should be the sum of the lengths of all such good words. For example, if adach are the available characters and cat is a word, we can form cat. A naive approach would be to iterate through each word. For every word, we'd convert the available chars string into a mutable list or array. Then, for each character in the current word, we'd search this list of available characters. If found, we remove it to prevent reuse and continue. If any character isn't found, the word can't be formed. This involves repeated linear searches and modifications on the chars list for every character of every word. This approach leads to a time complexity of roughly O(n) L*(m), where n is the number of words, L is the average word length, and m is the length of the chars string. Space complexity would be O(m) for the mutable character array. The key insight here is character frequency. Instead of repeatedly searching and modifying the available characters, we can pre-process the chars string into a frequency map, or more simply, a fixed-size array of 26 integers representing counts for a through z. This array will store how many times each character is available. Then for each word, we create a temporary frequency array for that specific word. We iterate through the word, incrementing counts for its characters. Once the word's frequency array is built, we compare it against our main chars frequency array. If for any character the word's count exceeds the available count from chars, then that word cannot be formed. Otherwise, the word is good, and we add its length to our total sum. This avoids repeated linear searches entirely. Let's trace with words as cat, bt, hat, tree, and chars as adach. First, we build our main frequency array for adach. A count is 2, t is 1, c is 1, h is 1, all others are 0. Now for the first word cat, we build its frequency array. C is 1, a is 1, t is 1. Comparing cat's frequencies to adach, c 1 less or equal 1, a 1 less or equal 2, t 1 less or equal 1. All good. Add 3 to total. Next bt, b is 1, t is 1. b 1 less or equals 0 and adach is false. Skip. Next hat, h is 1, a is 1, t is 1. Comparing h 1 less or equal 1, a 1 less or equal 2, t 1 less or equal 1. All good. Add 3 to total. Finally tree, t is 1, r is 1, e is 2. r 1 less or equals 0 and adach is false. Skip. After processing all words, our total sum is 6, from cat and hat. This is correct because only these two words could be formed using the provided characters, and their combined length is 3 plus 3. You'll spot this character frequency pattern whenever a problem involves checking if one string can be formed from another, or if character counts are a critical constraint. Concrete signals include needing to use characters, at most once, or problems asking about anagrams. It's a fundamental technique for string-based challenges. The time complexity is O(n) L, where n is the number of words and L is the average length of a word. Space complexity is big O of 1, constant time because our frequency arrays are fixed size, 26 integers. Mastering frequency arrays is key for many string problems. Try another problem involving character counts. Same pattern, different challenge. And don't forget to subscribe for more concise DSA explanations.